Hello again, welcome back. Today I'm going to tell you about directional derivatives. Let's go. So I'm going to start with a question that we already know the answer to. What is the rate of change of this function f of xy equals x squared minus y squared as you move through the point 2, 1 in the positive x direction? Well, we know for functions of more than one variable, if we want to find a rate of change as one of those variables is increasing and the other one's staying the same, then we just take a partial derivative. So the answer is we're going to take the partial derivative with respect to x at 2, 1. The partial derivative with respect to x of this function is 2x, and we're evaluating that where x, y is 2, 1, means we're going to get 4. Okay, so just so we have something to compare to, I want to take you over to GeoGebra so we can see what this number actually represents. So here's the picture in GeoGebra of the graph of the function x squared minus y squared. And I've marked here in this pink ball here, this is the point 2, 1. Actually, technically, it's the point on the graph that lies above the point 2, 1, the plane. So it's the point 2, 1, f of 2, 1. So here's this is the positive x-axis. This is the positive y-axis. Now, if we're taking the partial derivative with respect to x at this point, it's like we're fixing y. So we can think about it like we're taking a trace in the plane y equals 1. So I've added in that plane, and then the blue curve that you see here, that's the trace in the plane y equals 1. And what we're computing is the rate of change as we're moving along this path. So this slope here of this curve is the partial derivative that we computed. We can see that as you move in the positive x direction along this blue curve, the function's increasing, and indeed we did get a positive number for our partial derivative. So the next thing I want to do then is generalize this question a bit to ask, okay, we have the same function and the same point, but now I want to ask, what's the rate of change of that function at that point? Not as we're moving in the positive x direction, but as we're moving in the direction of a vector, in particular the vector -1, 3. This is what a directional derivative is computing. It's computing the rate of change of a function as you move in a direction that might not be the positive x or the positive y direction. It's a slightly more general idea. So the answer, I'm just going to write down the notation. We'll figure out exactly what the number is in a few minutes, but the notation for it, it's capital D. We put the vector as a subscript, and then the function and the point we're evaluating at. So again, this is the directional derivative. Back in GeoGebra, if we want to visualize that rate of change in that direction of that vector in the same way, we can do something similar. So here, I'm going to move the picture so we're looking at it from above just for a second. Looking at the xy plane from above, we want to think about moving through this point in the direction of the vector -1, 3. So that is, x is decreasing by 1 and y is increasing by 3. So we're moving along this line here. Maybe I can draw that in. So there we go. We're thinking about we're moving in the xy plane. The input is changing in the direction of -1, 3 through this point 2, 1. And if we look at the plane that lies above this line, so this plane here, then what we're doing is we're computing a slope of a trace in this plane. The only difference now is that the plane is not parallel to the xz plane or the yz plane. It's diagonal. So you can see here, as we go in the direction of that vector through this point, looks like the function, if we're looking at it from the side, it looks like the function's decreasing. So whatever we do to compute it down the line, we should expect to get a negative number. But before I tell you how we're going to compute directional derivatives, I just want to write down a definition in words and the notation again for reference. So the directional derivative of a function f of xy in the direction of a vector v at the point P, it's denoted, just like before, it's a capital D. Put the vector as a subscript, and then the function and the point at which we're evaluating the directional derivative. Again, the directional derivative measures the rate of change of f as you move through that point in the direction of the vector. A couple things to keep in mind is that if this is a function of two variables, then the point in question has to be a two-dimensional point, in other words, a point in R2. The vector v has to be two-dimensional as well. But you could also compute directional derivatives for functions of three variables. If you had f of x, y, z, then you'd want to be specifying a three-dimensional vector for the direction and a point in R3 at which you're going to evaluate. Okay, so now I'm going to tell you how to compute a directional derivative. And the formula might feel like it comes out of nowhere a little bit, so it might be worth it for you to take some time, either while you're watching this video or afterwards, to try to think about why the formula makes sense. So here it is. Again, if we're given a function, a vector v, and a point p, the directional derivative in the direction of v of f at p, we compute it like this. We'll take the gradient of f and evaluate it at p, and then we'll take the dot product, right? This is a vector, so we'll take the dot product of that vector with the unit vector in the direction of v. Again, this is the gradient of f evaluated at p. Check the previous video if you want a rundown about what the gradient is. And again, this is the unit vector in the direction of v. So you might see that in some sources, like some textbooks, they only define a directional derivative when the vector in question is a unit vector. But for our class, what we're going to say is we can take a directional derivative in the direction of any vector. It doesn't have to be a unit vector, but it's important that when we go to compute it, the thing that we dot with the gradient does need to be a unit vector pointing in the direction of v. Now that we have that formula, let's go back and finish this problem that asks us to compute the directional derivative in the direction of the vector -1, 3 of x squared minus y squared at the point 2, 1. We know now that we should take the gradient of f at 2, 1 and dot that with the unit vector in the direction of this one, the unit vector in the direction of -1, 3. So that will be -1, 3 divided by its magnitude. Its magnitude is the square root of 1 squared plus 3 squared, which is the square root of 10. Off to the side, the gradient of f, remember, is a vector consisting of the partial derivatives of f. So it looks like this. The gradient of f then evaluated at 2, 1 is going to be the vector 4, -2. So the directional derivative is 4, -2 dotted with -1, 3 over the square root of 10. And we can take the dot product of these two vectors and then divide by square root of 10. The dot product of these two vectors is going to be 4 times -1 plus -2 times 3. So it's -4 minus -6 over the square root of 10, which -4 minus -6, that's -10 divided by the square root of 10. So remember earlier, we predicted looking at the graph of that function and the trace that went through this point in this direction. Looked like that trace was decreasing as you moved in this direction, and indeed we did get a negative number as the directional derivative. Okay, so the last thing for this video is I want to answer the question, which direction v should we pick if we want to maximize the directional derivative of a function at a fixed point? So this point here, this point is fixed. To figure that out, let's write down the formula. The directional derivative we compute by taking the gradient of f at p and dotting that with v divided by its magnitude. So the goal is to pick v so that this is as large as possible. Okay, well, something that's helpful here is to use that cosine formula for the dot product, which says that another way to compute the dot product of two vectors is to take the product of the magnitudes of them, which is going to be the magnitude of the gradient of f, and then the magnitude of this vector, but the magnitude of this vector is 1, since it's a unit vector, so we can leave that out. And then the cosine of the angle between v and the gradient of f. If we want this to be as large as possible, then since we don't get to pick the point p, we really don't have any control over the magnitude of the gradient. And so all we really have control over is the angle between the unit vector in the direction of v and the gradient. And if we want this to be as large as possible, well, the largest cosine of theta can be is 1, and this is maximized when theta is equal to 0. In other words, we want to pick a vector v that makes an angle of 0 with the gradient. So why don't we pick v to be the gradient of f at p? If we do that, then we're guaranteed that this expression will be as large as possible because the angle between these two vectors is 0. So this is a justification of the first gradient fact from the previous video, which said that the gradient is the direction of greatest increase of a function. Now we have a better way to interpret that sentence. It means that the gradient is the vector that maximizes the directional derivative of a function at a point. And I'll leave you with this question to think about, which is, can you find a nice formula for what this maximum directional derivative would be? In other words, the directional derivative of f at p in the direction of the gradient of f. All right, so that's all about directional derivatives for now. You'll learn a lot more as you're practicing with them on the worksheets and in your P-sets. But besides that, I will see you next time.